Today, what I am going to see about the mechanisms of heat transfer, right? So actually, already we have discussed about we are worrying about not the bulk amount of energy, but the transfer amount of the energy, transferred amount of the energy. So energy can be transferred in two ways, isn't it? So both ways are work and heat. I change the color to black, so that will be work for you, right? Work and heat. Then we discuss about so many type of work transfer methods. So what are the forms of work, no? So electrical work and potential kinetic energy and elastic and so on. So many works we have discussed. So today what we are going to see about the heat transfer, right? So the mechanisms of heat transfer, in what are the methods that heat can be transferred to a system from surrounding, right? Or from the system to surrounding, whatever. So that is a transfer. So this is your system. So from the system or to the system, how the heat can be transferred. Okay. First one is conduction. We will discuss about the conduction. So the conduction is the transfer of energy from more energetic particles to the adjacent less energetic particles. That means, so as we discussed, if we are going into microscopic level, so molecules are there, right? So molecules or atoms or whatever. Okay, so those are called as particles. In those particles, from the more energetic particles mean, so if we take if we take a molecule, so the molecule will have an internal energy, isn't it? So due to the uh, electrons motion and its own motion and vibration, so those on stuffs that is going to have an energy. Okay, so different molecules, so this one is A and this one is B. It could be a molecule or particle or whatever, right? So this is another particle B. So let's say A is having, A is a more energetic particle. Okay, A's energy is higher than B's energy, EA, EB. So when they are interacting, that means when they are touching or something, the energy will transfer to A to B. Okay, let's assume EA is greater than EB, right? So when B is coming near to the A, right? So then heat will energy will transfer to A to B, right? So when this A is having more energy, right? Then when this A is having more energy, that means the A's temperature is higher than B's temperature, right? So that is how we can say which one has more energy, right? Let's take a cup of water, right? Cup of water in room temperature and another cup of water that is in 100 °C. So this 100 °C water molecules will have more energy than this room temperature water molecules, right? So this 100 °C, so the I name it as B and this as A. So this B will have more energetic particles, right? So because they are having more temperature, okay, temperature measurement. Okay, in other way also, when B's particles are having more energy, the temperature of the B is increased, right? So that is how you can say which one is more energetic, which one has more energetic particles, right? So there's a equation for the, yes, someone raised your hand. Do you want to talk something?
Sorry, sir, it's a mistake.
Okay. So heat conduction equation. Heat conduction equation actually describe the phenomenon of the heat conduction, how the heat is conducted. Okay, so what amount is conducted, or the what amount is transferred, right, due to the conduction, right? So this will give us the amount of heat transferred in a given rate. Okay, so this is a rate equation. You can see that Q dot is there. So Q dot means that is a rate, heat transfer rate. That means in a unit time, how much heat is transferred. Okay, in a unit time, how much heat is transferred. So that is the equation. You should know this equation. So in when there is a heat conduction problem is coming, so you should use this equation, right? So this is not a hard equation. You might have studied this one earlier in your A levels or O levels, isn't it? Q dot conducted is equal to Ka delta T over delta X, right? K mean if you take a wall or something, right? So normally for the heat conduction, we talk about solids, right? So heat conduction can occur in all three phases. It can be in solid or liquid or gas. Okay. In any phase, this conduction can happen, right? We will discuss about the liquid in how the heat is conducted in liquid in gas is later, right? Later on this session. So let's talk about the solid here. Okay, when you are having a wall, right? This we know the driving force of a heat transfer is what? What drives heat transfer? So the temperature difference, isn't it? Okay, if there's a temperature difference, heat transfer will occur, isn't it? Right? So I walls this side is temperature 2 and this side is temperature 1. Let's say, so this is a wall, cross section of a wall, right? Or your room wall, whatever, right? So outside temperature is, let's say, uh, what is today's temperature? What's today's temperature? 31 degrees Celsius. Okay, let's say 31 degrees Celsius. Okay, so this is inside. Okay, so that this is outside, this is inside of your room, right? Inside of your room. So that inside temperature, let's say you put an AC and keeping in 23 degrees Celsius. So as an example, so heat is going to transfer from outside to inside, right? Outside to inside. So this is your heat transfer direction. This is your heat transfer direction, right? So the amount of heat transferred during a unit time. Okay, let's say in 1 second. Normally unit time we take as a 1 second. So how much heat is transferred is, we can say with Q, conduction is equal to K. K is a property of this wall, right? Property of this wall. That is, I'll tell you about the K later, right? That is a conduction property of this wall. A is the area. Okay, A is the area exposed. Okay, area exposed to heat. That means your wall surface area, right? Into delta T. Delta T is the temperature difference. Okay, so higher temperature is T2, lower temperature is T1. That is the temperature difference, delta T over delta X. Delta X is the wall thickness. Okay, what is the distance of heat conduction, right? So what is the actual distance of the heat conduction occurs? So this is the delta X, that is the length of your or length of your thickness of your wall. Okay, from the wall cross section this is happens now. So the length is the thickness of your wall, delta X, right? So that is the actual heat conduction equation. So K is the thermal conductivity, right? So the property of this wall is called as thermal conductivity. For every materials, this thermal conductivity value is available, right? So the engineers has find the values for the thermal conductivity. So you don't need to worry about what is the thermal conductivity. Sometimes if it is a composite wall, you have to calculate by using the some techniques are there, but up to that level we don't want to go there. Okay, so you can we can study about the same material. Okay, so if the wall, then we just worry about the concrete. Okay, not about the what is the paint thickness and what is the cement thickness, and is it sometimes we might use cement and this bricks, no? So when we are using that one, that will differ. Okay, plaster wall, those are some complicated stuff. Okay, we don't want to worry about that one. We will study about the pure materials. Okay, pure materials mean only one material. So let's say concrete is a one material, or if it is a steel is a one material, or copper or whatever, because sometimes you don't want such bigger issues. Okay, so we will study with the only one material, right? So that is a thermal conductivity in your problem, that is always available. Okay, you don't want to worry about this thermal conductivity, that will be given, right? So this is actually called as thermal heat conduction equation, right? Heat conduction equation. Actually this equation is from Fourier's law of heat conduction, right? Fourier's law of heat conduction. Sometimes you might have went through this Fourier's law. I think as a worksheet I have given, everyone write there and put your equations there, and get some pictures from the internet and put there. I don't sure everyone has studied or read it and put there, right? So the Fourier's actually describe this heat conduction, okay, with this equation. So you can see a minus here, so that is actually the difference. So why we are putting a minus is, right, so you can use any of these two equation. Okay, so Fourier's heat conduction equation also you can use, or this one also you can use, right? So the same thing is here, but we are assuming, right, for a, so if we say, let's say the wall thickness is this much, right? I put as x, okay, but Fourier did this. Fourier just get a small differential element delta x, okay, small differential element from the cross section of this wall, right? And for that one, so delta x, so here one temperature T1, T2, okay, here and I put a small dash, okay, for the difference. Here outside T1, T2, okay, so the inside component there is a small, so here temperature is going to change all over the space, no, here one temperature, here another one, here another one, for every each small sections temperature is going to change until T2, until it reaches T2, right? So when he get this small differential component, right? So this is, so delta T1 dash T2 dash minus T1 dash delta T or the dt, right? Sorry, that is actually capital T, dt, that is the temperature difference, okay? So what is he is actually doing is, he is earlier he is defining that this is the heat conduction direction, okay, without seeing any temperatures, okay, without checking any temperature. Here we put delta T as T max minus T minimum, okay, but here he don't check what is T max or T minimum. He just put this is the heat conduction direction, so the del dt is T2 minus T1, right, for this heat conduction equation, okay? So if the answer is coming in minus, right, if your answer is coming in minus, your assumed direction is wrong, okay? That means if you assumed in this direction and coming with a minus sign, so your direction should be this, okay? If your answer is coming in positive value, then you assume direction is correct, right? That is the only difference. But when you are using this heat conduction equation directly, you are already know in which direction heat is going to conduct, okay? That is T max minus T min, right? So that is the only difference between that equation and this equation, okay? So then I already said that in all phases, right, in all three phases, that is solid, liquid, and gas, all three phases, principal phases, this conduction can happen, right? So if you take a fluid, okay, if you take a fluid can be a liquid or gas, okay, fluid can be a liquid or gas. Solid is this one, right? So if you take a fluid, so that is having a random motion, okay, so that is not actually connected well, okay. We will talk about how these things are connected and the motions and everything later in another session. So in basic, you know this one, no? So this liquid and gas having, liquid is similar, slightly packed, but they are also having random motion. But if you take a gas, they are not connected. They are moving always random movements, isn't it? So when you are take a conduction process in liquid and gas, right, from high energetic particle to low energetic particle, so when they are hitting them, right, when they are moving here and there, they are hitting. So because of that phenomena, right, because of that phenomena, this heat conduction happen. Okay, but for that conduction for this liquid and gas, you should keep the fluid in a barrier. Okay, you should restrict the movement of the fluid. That means, so let's say if you have a small block or something, okay, so that is in a higher temperature, 100 degrees Celsius, and if you flow the air, we can't say that this is conduction because the air is flowing. Okay, but if you have this kind of an object in a closed place, okay, so that this air can't move anywhere. Okay, this air can't move anywhere. Here you are keeping a higher temperature object, something connected with that box. Then we can say that this here conduction is happening. Okay, same for the liquid also. So you should have a barrier. Okay, that is restrict the movement of the molecules. Then pure conduction will occur. Otherwise, that's a phenomena is called as convection. That is what we are going to talk about next. Okay, but it's about the convection. Convection will happen, right? So from the so what how the conduction happens is here. So let's say you are having a ball, right, that is moving slowly or that is not moving. Okay, that is not moving. Then you are hitting that ball with another ball that is moving fastly. Okay, this is moving fastly. Let's say velocity is 5 meters per second. When this ball A is hitting ball B, what will happen? When this ball is hitting B, what will happen to the velocity of B? Can you hear me? Hello.
Yes, sir, can hear.
Yeah.
Yes, sir.
Yeah. What
Yes,
will
sir.
happen? These are same mass. Okay. Same mass, and A and B is velocity is 0. Okay, that is in rest. That is at rest, and this A is traveling in velocity 5 meters per second and hitting B. What will happen to the velocity of A and B? What is your idea?
B increase, sir, A decrease.
Yes. So what happens there? A's energy is reducing, B's energy is increasing. But you know, the total energy will be conserved. Okay, the energy from A will transfer to B, right? That is actually happening liquid and gas when the molecules are hitting. Okay, more energetic particles hitting the low energetic particles. Low energetic particles will get higher energy, right? Higher energy than earlier, and higher energetic particles will lose the energy to low energetic particles. So then what will happen when a particle's energy is increasing? That means the temperature is increasing. Okay, so that is how heat is transferred to particles, right? If you take a solid object, we say that as a the atomics arranged as a lattice. Okay, so in a solid, atoms and molecules or whatever are arranged well. Okay, they are arranged well. So in the solid, two ways are possible to translate the or conduct the heat. Okay, that means, so if they are also arranged, they will be vibrating. Okay, atoms or molecules are vibrating. So what else? So that is depend the vibration amount is depend on their internal energy. When the particles are having higher amount of energy, they will vibrate very fast, right? Vibrate very fast. So that vibration will cause what? That will touch the another particle. So when they are touching the another particle, what will happen? That vibration will transfer to that one. The same thing happened to liquid. Okay, so this vibration energy will transfer to another thing, another particle. So that will get a vibration. So that means that's energy is increased. So that is how nearby particles will get the energy. Okay, then particles getting the energy, heat will temperature will increasing. Okay, increasing for those particles, and heat will transfer in that direction. Okay, because of their atoms or molecules or whatever's work, or those particles work. Okay, work is, that is, vibration is actually the work. Okay, but when you are seeing macroscopically, so that will be a heat transfer. Okay, that will be a heat transfer. In another way of transferring heat is there in solids, mostly in metals, right? In metals, how the arrangement is, atoms are like this. Okay, they are closely packed, right? Those in metallic bond, there is free electrons are available. Okay, free electrons are moving everywhere. Okay, moving around everywhere. So in solids, in metals, those free electrons will carry the heat. Okay, will carry the heat to one place to low high energetic place to low energetic place. In that way also, this heat conduction will happen. Okay, that is behind this conduction. So all those two ways for this solid, and you know what is about what's happening in the liquid and gas. Okay, so what you should know is this equation. Okay, so how to use this equation also. Next one is convection. Convection, I have already told you, it's likely conduction. Okay, the phenomenon is conduction is actually happening, but how the name is changes is there is a fluid flow. Okay, fluid in motion. So that fluid can be a liquid or gas. Okay, that should have a motion, right? So that means that fluid should take the heat, receive the heat, and release it to somewhere less heat. Okay, so that is actually called as convection. For an example, okay, so let's say you are having your meal. Okay, so that is very hot. Okay, when your mother made the meal, so the meal is very hot. Okay, rice. So rice in 60 or 70 degrees Celsius. So you keep it in your table. Okay, when you are keep it on your table and switch on the fan, right? You are switch on the fan. So air molecules come from the fan and receive the heat from your whatever your meal and goes away. And then new particles will come and receive the heat and go away. Likewise, your meal's total energy or the temperature is going to decrease because of the fluid motion, right? That is actually called as a fluid motion. So there should be a fluid motion for this convection, right? So there's a small example is given here. There's a hot block. Okay, it can be a let's say a iron block. Let's say iron block that is heat up to a certain point. Then for cool down it, you are blowing the air. Okay, you are blowing the air. This is a velocity change with the x. Okay, so this is the in this direction distance, and this is velocity axis. So velocity changes with the this direction. Okay, this is how the velocity variation. Okay, velocity variation. So you are flowing the air velocity. So if you take this point, air velocity is 0, right? Air velocity is 0. So another graph is given, that is temperature with the distance. Okay, temperature with the distance. That is how is TF is the outside your air temperature, your air flows temperature. Let's say that is in room temperature or whatever. So TS is the surface temperature of the heat block. Okay, that is going to change in this way. Okay, so you can see there is a relationship with those. When the air flows velocity is increasing, the convection effect will increase. Okay, that will carry more heat from the hot block, whatever your hot object, right? So the faster the fluid motion, the greater the convection heat transfer, right? So that means when you are increasing your fan's velocity, you know, you can cool your meal quickly, isn't it? Okay, if in the absence of, this is the important thing, in the absence of any bulk fluid motion, heat transfer between a solid surface and the adjacent fluid is by pure conduction. Okay, it's by absence of any bulk fluid motion. So that is what I already said you. If the fluid is not moving, then that is pure conduction. So sometimes we are having this. Okay, sometimes you might see this kind of bricks, isn't it? Have you seen this kind of bricks, the cross section in some walls? this, there's a air hole for the bricks. Have you seen?
No, sir.
Yes, sir.
No, nobody seen this kind of bricks. There's a hole for air. No
Yes, sir.
material. Yeah.
Sir,
Okay.
yes, sir.
Anyone
Yes,
see?
sir.
Yeah.
Yes, sir.
Because the air has low conduction. Okay. Low conductivity. K. Okay. But air can air can remove a lot of heat because of convection. Okay. Because of the convection, air can remove a lot of heat from a place. But air's conductivity is very low. If we take the air and if you are not making in any motion for the air, that's a conductivity is very low, right? So heat loss will be decreased. So that's why we are having this kind of bricks for the construction. Okay, so if you put the cement to this brick, what will happen? The inside air will move, air will not move anywhere. So the motion of the air will restricted. So the conductivity of this brick is reduced, right? So when the heat is coming from outside from inside, this amount of heat transfer Q dot will be, when the K going low, Q dot will go low. Okay, so amount of heat transferred inside your room will decrease. Then you will feel more cooler than other brick types for this one, right? So that's why we are having, sometimes the people will use this type of bricks. Okay, so this is another example for this for convection. So you can see two terminologies for the convection. One is forced convection and natural convection, right? So for forced convection is you are using a external force to pump your fluid motion. So that means that could be a pump or fan or whatever. Okay, where when you are using that kind of external pumping, so that is called as forced convection, right? So sometimes when you are cooling with um, water, you are using pump. Okay, so in your engine cooling system, we are using water pump, isn't it? Water is going and take the heat and release it on the radiator, isn't it? So the fluid, there's a fluid motion that receive the heat and going somewhere and release it and coming again and receive the heat, and that is a cyclic process, right? So natural convection is, so that is because of the, so you are not using any external source to force the fluid motion. Okay, so due to the what's called as the density changes. Okay, so you know hot molecules have more less density than cold molecules, isn't it? Not the molecules, the substance. Okay, so if you take hot air, if you release the hot air, that hot air will always move upwards because the density of the hot air will decrease, because when you are making it hot, that will expand. Okay, the space between molecules will expand. Okay, so have you heard about the hot air balloons? hot air balloons? Not yet.
Yes, sir. Here.
Yeah, this one. Yeah. So you are heating the air and leaving it in the atmosphere, that will move upwards. Okay. So that is because of the density change. For this one also, if you are keeping a hot food on or hot egg on your table, what will happen? The air molecules near to the hot egg will receive the energy from the egg, and that will, the energy of the air will get increased. Okay, because of the energy increased, temperature will increase. When temperature increase, that specific volume will increase, right? Volume will increase, and they will tend to, the density will decrease, they will tend to move upwards. So there are some less energetic particles on the top, they will tend to come downwards, and they will receive the heat from the hot source and going there and release it and coming here. Okay, so this is called as the natural convection. Okay, so for this convection process, Newton actually have a law, right? He has developed a law and the equation for the convection. So that is actually called as Newton's law of cooling. So this is actually the Newton's law of cooling. So here also rate of heat transfer, right? Rate of heat transfer. So that is H A Ts minus Tf. Ts is surface temperature, Tf is outside or your atmosphere or whatever your fluid temperature, right? Fluid, whatever the fluid you are using. Okay, Ts is surface temperature. That is the hot source surface. Okay, not the core. So if you take a egg, so inside the egg there is a different temperature. So here different surface temperature will be different one. Okay, so this core will have different temperature and surface will have different temperature. And this core to surface, what will in which mechanism heat will transfer? That is conduction. Okay, up to the surface for egg. After this, convection will happen, right? If you keep it in a table or whatever. H is called as convection heat transfer coefficient. Convection heat transfer coefficient. And A is the surface area through which the heat transfer take place. Okay, let's say you are having a hot block, that is heat is transferring. The shape is like this. Okay, but you are sealed all other stuffs behind this. This is only exposed. Okay, this area only exposed to convection heat transfer. Other areas are not exposed. Then you have to put this area. Okay, if you put the block like this, okay, block like this, and you put the airflow like this, when what is the heat transfer area? All the surface area around the box. Okay, that is exposed to heat transfer, right? So the bottom part will not come. Why? That is not actually transferring the heat with the convection heat transfer, isn't it? So that is actually sometimes that will conduct the heat to the table, right? So you shouldn't put that one, right? Whatever the exposed area to convection, you should put, right? That is the surface area through which the heat transfer takes place. Ts is the surface temperature and Tf is the bulk fluid temperature away from the surface. Okay, that is the bulk fluid temperature. Heat transfer process that involve change of phase of a fluid are also considered to be convection. Okay, so phase change means, so sometimes your water will boil and come to a phase, gaseous phase, isn't it? So water earlier in liquid, and that will change to gaseous. So when that phase changing is occurs, can you hear me? Hello?
Yes, sir.
Okay. When the phase changes occurred for a fluid, that also considered as to be a convection, right? So sometimes gas can release the heat and become as a liquid. Okay. So if you close your, if you are boiling your water and close it with the lid, right? If your water is boiling, if you close with the lid, what will happen? The gaseous water vapor will condensate on your lid, isn't it? So that also a phase change from liquid to gas and then gas to liquid again. Okay, so there's again and again phase changes happening. So such phase changes happening in a process or heat transfer process, right? That also considered as convection. Next one is radiation. Radiation, sometimes you might heard about this one. So normally what's the main radiation stuff you are receiving? Radiation heat energy you are receiving via from the sun, isn't it? From the sun, there's a very important radiation energy we are receiving. So that's you people are know the energy emitted by matter. Okay, so energy should emitted by a matter. So that matter can be in any phase. Okay, matter can be in any phase. Matter means that could be a solid, that could be a liquid, that could be a gas. Okay, any major phase it can be, right? And emitted by a matter in the form of electromagnetic waves. Okay, in the form of electromagnetic waves. So that is actually called as radiation. Or now if we are talking with the quantum field, that will be called as photons. Okay, so that's also a particle that called as photon. Or electromagnetic wave is also okay, right? As a result of changes in the electronic configurations in the atoms or molecules. Okay, when this line is little bit deeper, if you are having some little bit of deeper knowledge in physics, you can understand this one, right? So electronic configurations of these atoms or molecules when they are changing, okay, when they are the orbiting these tiles are changing, okay, here and there, that will release the photons. Okay, so this is your atom core, and you are having orbits, different orbits are there. When the orbits are changing for the atoms, okay, so those will emit the electromagnetic waves in different wavelengths. Okay, so I don't want to talk about this lot more, then you will be confused, right? So those electronic configurations changing, those will emit the electromagnetic waves. Okay, electromagnetic waves that is start from UV to radio waves. Okay, UV to radio waves, there are a lot of waves in different wavelengths. Okay, so you can define a wave with the wavelength or frequency. Okay, whatever is okay. You can state with the frequency or wavelength, because lambda into f will give you the velocity of electromagnetic wave. For the velocity of electromagnetic wave is equal for all waves. Okay, when lambda increases, it going in this way. If frequency increases, this will go in this way. These some things sometimes you might have studied this configurations in how to chart this one in science for technology, I think. Sometimes, so we are not worrying about all these waves. We are worry about this heat wave, right? So for this electromagnetic waves or the radiation, we don't need any medium. Okay, so for the conduction and convection, we need medium. Okay, we need medium. So medium mean in the phase of solid or liquid or gas, in any phase we need somehow a medium. For the convection, we need a bulk amount of fluid motion. Okay, that is the medium. So the conduction, we are worrying in the solid phase, right? That also need a medium, any medium. So but for the radiation, we don't need any medium. You can transfer the heat as a radiation form in a vacuum also, right? In vacuum also. If you take a thermos flask, okay, thermos flask, everyone are using flask, no? Inside the flask, there's a glass structure is there. Okay, outside plastic cover and plastic lid, and inside a glass structure is there. So if you put the flask on the ground, then that will break, isn't it? You know, do you know it?
Yes, sir.
Yeah.
Yes,
So
sir.
actually in the glass structure, what they have did this. So the glass structure having two layers. Okay, one is glass and inside of that is vacuum. Okay, inside of this area is vacuum, and after the vacuum they are having a mirror kind of coating. Okay, mirror kind of coating, right? So due to the vacuum, what will happen? Your heat will not conduct. Okay, and convection also will not occur. Conduction or convection, as this is closed, no convection there, only conduction is possible. But because of the vacuum, there is no particles to carrier or medium is carrier. Okay, your heat will not conduct and you are having a mirror kind of coating. Then what will happen? electromagnetic waveform in radiation, without the medium, radiation can get your heat outside. If you put a mirror coating there, what will happen? That will reflect again to inside, isn't it? So that is also you are preventing, right? So as you are putting a lid there, again you are preventing the effect of convection, right? So no fluid bulk motion. So that is the idea behind this thermos flask, right? So for this one, what is the important thing is, so no medium is required. All bodies at a temperature above absolute zero emit thermal radiation, right? So that means absolute zero mean 0 Kelvin. 0 Kelvin mean minus 273 degree Celsius. Okay. So if any bodies more than this temperature will emit the radiation. Okay. Emit thermal radiation. So actually where this is possible? Absolute zero. Nobody find this one yet. Okay. In a universe, in a given black hole, they have find minus 10 to the power minus 27 degree Kelvin. Okay, but they couldn't find the absolute zero in universe also. Okay, this one 10 to the power minus 27 they have found. Okay, but the absolute zero they couldn't find. So you should know all the objects having thermal radiation. You are having thermal radiation. Your whatever the objects in your table have is doing thermal radiation. Whatever the objects in the universe also having thermal radiation, right? The maximum rate of radiation that can be emitted from a surface at an absolute temperature Ts, okay, that's from a surface, given by the Stefan Boltzmann law, right? Actually, the Stefan Boltzmann put the idea about this thermal radiation, and he got a law for the thermal radiation. The law says Q dot emit maximum, okay, maximum emittable thermal radiation, that is equal to sigma A Ts to the power 4, right? Sigma is Stefan Boltzmann constant, okay, that is a constant. A is the surface area, Ts is the surface temperature. Okay, so this is actually the Stefan Boltzmann constant, right? This amount. So the idealized surface that emits radiation at this maximum rate is called as black body. Okay, so an ideal surface. Okay, so actually that is a maximum amount of radiation can be emitted by any object. Okay, so then that object will called as ideal object. Ideal object, that is black body. Okay, only the black body can radiate that much of heat from its surface, right? But other bodies are having lesser than that, right? So the body is having radiation. The black body's radiation is called as black body's radiation is called as black body radiation, right? So the maximum amount of thermal radiation that can emit right? For a ideal body. Okay. The radiation emitted by all real surfaces. Real surfaces mean not the black bodies. Okay, not the black bodies, the real surfaces. Your body or whatever, your table or whatever the real body. Okay, real surfaces. So that can be expressed as the with the epsilon. That is emissivity. Okay, for the black body radiation, you should multiply it by the emissivity, epsilon. Okay, so the epsilon property can be changed with the 0 to 1. So when the epsilon reaches 1, that is called as black body. That is the ideal surface, right? This is the emissivity. So another one is absorptivity. So that means, so as the objects are emitting electromagnetic waves, okay, so you are emitting electromagnetic waves, and if you go to sunlight, you will receive the sunlight. You will receive the sunlight also. At that time also, you are emitting your electromagnetic waves. Also, you are receiving the sunlight. Okay, that means from the external sources, from the external objects, they are releasing electromagnetic waves, the heat waves. You are receiving that also. Okay, you are receiving that waves also. So that is absorbing. Your body is the part of the radiation will absorbed by your body. So then sometimes you might feel hotter in your skin, isn't it, when you are exposed to sunlight, right? So if you keep any object in the sunlight, if you touch it, you can expose to sunlight. When you are touching that one, you can feel the heat absorbed by that object, isn't it? At the same time, that object also, because of that temperature of that body, that also emitting the radiation, right? So when you are absorbing there, absorptivity alpha is there for each and every object. Okay, because of the surface properties. Okay, this absorptivity and emissivity is depend on the surface properties. Alpha is the function of the radiation energy incident on surface that is absorbed by the surface, right? The same what I have told you. Like emissivity, its value is range 0 to alpha, right? 0 to alpha. So when alpha is equal to 1, that is called as perfect absorber. That is also the black body. So the black body is perfect emitter and perfect absorber, right? So here you can see that in a surface, Q dot incident is there. Okay, Q dot incident mean whatever the electromagnetic energy or the heat wave is coming to the surface, and part of the surface will be absorbed and another part of surface will be reflected. Okay, for the absorbed one is you have to the incident with the incident you have to multiply it with the alpha value of the surface, whatever the surface, right? Then whatever remaining, that means 1 minus alpha into q dot incident, that will be reflected. Okay, that will be reflected. When you are seeing about this radiation, right, the object also object A is there, object B is there. Okay, A also releasing heat energy, okay, in radiation. B also releasing. A will get from B, also B will get from A. Okay, what defined from which one is actually receiving more heat energy from whatever the object, that depends on the their amount of radiation. Okay, so then we can say in the net which one received and which one emits. Okay, so that means A emitted q dot A, B emitted q dot B. Okay, then let's say q dot A is less than q dot B, right? Then q dot net is equal to q dot B is greater than, so q dot B minus q dot A. Then what will happen? This amount of energy A will receive. Okay, A will receive this amount of energy. Also, B will emit this amount of energy, right? So both two objects are having the thermal radiation. Okay, thermal radiation both objects are having. Okay, so because due to which one is having higher energy, okay, higher energy radiation or higher radiation, we can say what is the net amount of thermal radiation. Then we can say which one received and which one emits. Okay, so there's a law for the radiation, that is Kirchhoff law. So Kirchhoff law is what I have discussed here, right? What I have discussed here. Q dot whatever amount of absorbed heat is equal to alpha into q dot incident. That is the Kirchhoff law. The difference between the rates of radiation emitted by the surface and the radiation absorbed in the net radiation heat transfer. This is what I have discussed here. Right. So this small body is radiating, right? Radiating to the surrounding. The surrounding molecules also going to radiate it. Okay. So the net will give is which one having more heat intensity, right? Or the more amount of heat is rejected. So the radiation heat will give sigma epsilon also there. Okay, that is emissivity sigma A. The bodies, the small bodies radiation is T surface to the power 4 T surrounding to the power 4, right? This will be the net amount of radiation for this object, right? So this is about the radiation, right? So you can change with the other stuff. Okay, sometimes there's a object like this, and your surrounding, this is low temperature, your surrounding is high temperature, then heat energy will be received by the object, isn't it? So then this will change. Okay, you will get the answer in minus value. That means the radiation heat transfer direction is wrong. Okay, so surrounding to surface. If the surface is having more higher temperature than surrounding, then from surface to surrounding, then surrounding to surface. So that depends. Okay, for two bodies also you can discuss with them. Okay, two bodies also you can discuss. So let's say two objects are there, A and B. So net amount of energy is transferred between them due to the effect of thermal radiation. Then you can calculate what is the area for them, right? A to B or B to A, whatever the depends on the temperature, right? Depend on the temperature, you can discuss with the same equation, right? Okay, this is related to the heat transfer mechanisms. All three stuff, that is conduction, convection, radiation, right? So now you are having collective of equations. Okay, these are not that much of hard. Okay, you should know the equations and you should know how to apply those equations to the given questions. Okay, I didn't go so much deep on this conduction, convection, radiation, because you don't need actually this energy transfer mechanisms. You know, you should know, but you don't want to know the very deeper ideas about from the molecules to these electronic configuration. So much the deeper stuff you don't want to worry about those things. Okay, you should know how to use these equations in the actual real world problems. Okay, so because when you are having this cooling systems and heat receiving systems and these air conditioning or whatever, then you should know about little bit about this heat transfer mechanism. Okay, then only you can think about how the system works. Okay, so actually we are studying this thermodynamics to understand how the thermodynamic systems are working. Okay, so if you take a automobile, so there are a lot of thermodynamic systems are there, as I told you earlier. Okay, so if you have the knowledge about this thermodynamics, only you can understand what is actually happening in the systems. Okay, okay, any doubts? Hello,
No, sir.
anyone having any doubts?
No, sir.
No, sir.
No, sir.
Okay. Then we will end this session.
Okay, sir.
Okay.
Okay, sir.
Okay, sir.
Okay, sir.